All right, get ready to explore something pretty amazing today, something super tiny but incredibly powerful. We're diving deep into the world of molecules.
That's right. We're talking about the most fundamental building blocks of, well, everything around us.
And you sent us a really cool mix of stuff about this physics lectures from like over 100 years ago, cutting edge research on this new molecule called lake. So, wow, where do we even begin with all this? I guess my first question is, were molecules always this mysterious? Like, did we always even know they existed?
Well, our understanding of them has definitely evolved, that's for sure.
Right.
Imagine it's 1873. You're sitting in on a lecture by physics superstar James Clerk Maxwell.
Go.
And he's talking about these tiny units of matter. So small they were totally invisible, even with the most powerful microscopes back then.
Oh, wow. So how did they even know molecules existed if they couldn't see them? That's kind of wild to think about.
It was like a puzzle, right?
Yeah.
They were putting it together with experiments and deductions and such. But get this. The debate about what matter is actually made of, like the very essence of it, that debate had been going on for centuries by that point.
Really?
Centuries.
Yeah, we can trace it all the way back to ancient Greece.
No kidding.
Yeah, seriously. And they had some really different theories back then.
Like, what were they thinking back then?
Well, you had Democritus, who was all about atoms. He thought atoms were like these hard, unbreakable little particles, the absolute smallest piece of anything. Like the buck stops there, Can't get any smaller than an atom.
Right, that makes sense to me.
Right. But then you have Anaxagoras coming in with a totally different take.
Oh, really?
Oh, yeah. He was like, no way, you can divide matter forever. He called this idea homohomoeity, which basically means any substance is made up of parts that are exactly like the whole, just smaller.
So, like, if you take a drop of water and split it, you get two smaller drops of water, and you could keep doing that forever.
Exactly. No limit to how small those drops could get.
Which, as we know now, isn't quite how it works, right?
Yeah, science has come a long way.
It really has. But it's still fascinating to see how those ancient thinkers were wrestling with these really big questions about, like, the fundamental nature of reality.
It really is. It kind of makes you think we're still doing that today, aren't we? Just on a much, much smaller scale now.
Absolutely. We're always searching for those fundamental truths.
Yeah, trying to understand the universe, one tiny piece at a time.
Exactly. And fast forward to the 1870s with Clerk Maxwell, things really started heating up in the world of molecules.
So he was the one who finally proved molecules existed then, or were people still unsure?
Well, not all the answers, not quite. But he was definitely onto something big. He was one of the first to really make a clear distinction between atoms and molecules, which you mentioned that in your notes, right?
Yeah, I did notice that the word molecule seemed to pop up more in the modern research, while the older stuff seemed to use atom for, well, pretty much everything.
Right.
So what's the difference, really?
Well, it all boils down to how these tiny particles are arranged, you see.
Okay.
Think of an atom like the most basic ingredient, the simplest element you can have, like a single Lego brick, right?
Okay.
An atom of oxygen is just that, pure oxygen, nothing else.
Yeah.
But a molecule, that's where things get really interesting.
All right, so a molecule is like combining Lego bricks to build something bigger.
You got it. It's when two or more atoms decide to team up and form a bond, like that water we were talking about earlier, H2O, two hydrogen atoms and one oxygen.
Right.
Linked together in a very specific way, and that's what makes it water.
And that specific combination, that's what gives it its properties.
Exactly. It's mind-blowing when you really think about it. Like everything around us, the air we breathe, the cells in our bodies, it's all just different combinations of atoms.
Wow.
Arranged in these crazy, intricate molecular structures.
Yes, like a molecular dance, kind of.
Yeah. And get this. This is what really blew people's minds back then. Clerk Maxwell, he proposed that these molecules aren't just static things.
They're not.
No. They're in constant motion, even in objects that seem perfectly still.
Hold on, so even in this table I'm touching,
Oh, yeah.
the molecules are moving, but I don't feel anything.
Oh, they're moving all right. He used this really cool image to explain it.
Okay.
He said to imagine the air molecules in a room zipping around at 17 miles per minute.
17 miles per minute, wow. Why aren't we like blown off our feet by this constant molecular hurricane?
Because it's coming at us from every direction. It's like imagine a massive swarm of bees, right? All buzzing around chaotically.
Okay.
You're getting bumped from all sides constantly, so it all balances out.
Ah, okay, so no net impact.
Exactly.
So what happens when you introduce a new type of molecule into the mix? Like, say I spill my coffee. How do those coffee molecules know to like spread out and create that aroma that fills the whole room?
You've just hit on one of the most fundamental processes in the universe.
Diffusion.
Diffusion.
Right.
Remember those bees? Now imagine some of them have flour on their backs. As they bump around randomly, they spread that flour everywhere without even trying.
So the flower is like the smell, and it's spreading out just by the random motion of the molecule.
Exactly. And Clerk Maxwell, he didn't just throw this idea out there. He actually backed it up with real-world examples. Think about how heat travels. That's diffusion in action. Or how a drop of food coloring in water slowly spreads out to color the entire glass. Diffusion again.
It's happening all around us.
All the time, yeah.
Wow. But I have to imagine diffusion happens at different speeds, right? Like, wouldn't a gas spread out faster than a liquid?
You are on fire today. Clerk Maxwell, he noticed that very thing. He had this clever demonstration to show how diffusion speed changes between gases and liquids.
Oh, really? What was it?
Okay, picture this. You drop some copper sulfate into a jar of water.
Okay, like it creates that cool blue plume that kind of descends and spreads out?
Exactly, that slow, graceful spread. That's diffusion in action. But in a liquid, the copper sulfate molecules are trying to spread out, but they're constantly bumping into water molecules, which slows them down.
So it's like trying to navigate a crowded room versus running through an open field.
Perfect analogy. In a gas, the molecules have way more space to zoom around, but in a liquid, it's like rush hour. They're packed in tight.
Makes sense.
And this difference in diffusion rates, it's incredibly important.
It is.
Oh, yeah. It affects everything from how quickly a smell disappears to how efficiently oxygen gets to our cells.
You know, we've established that molecules are constantly moving. They're spreading out through this diffusion process. But I'm still stuck on the fact that these things are so incredibly tiny. How in the world did scientists even begin to study something so small, especially back in the 1800s?
It really is amazing, isn't it? Clerk Maxwell, he had to get creative.
He did.
He introduced this idea of a mean path.
A mean path. Okay.
Basically, the average distance a molecule can travel before it bumps into something else.
So like that crowded room thing again?
Exactly.
Right.
Only now we're talking crazy small distances here.
Right.
Clerk Maxwell, he actually put together this table in one of those lectures you sent.
Okay.
And the numbers, well, they're really something.
How small are we talking exactly?
Okay, so get this. If you lined up millions of hydrogen molecules end to end,
Yeah.
you'd barely span a single millimeter.
Wow. And hydrogen is the smallest element, right?
The smallest.
Yeah.
It's almost impossible to imagine, right?
It really is.
But hold on, it gets wilder.
Okay.
He estimated that a single cubic centimeter of gas,
Okay.
like picture a tiny cube of the air we're breathing right now,
Yeah.
that tiny space contains 19 million molecules.
19 million. Are you serious? That's got to be more than all the stars in the galaxy, right?
It might be. The point is, it's an insane number. Even now, it's hard to wrap your head around.
Absolutely.
And Clerk Maxwell himself, he admitted these were, rough estimates based on the data they had. But still, those numbers, they gave scientists a glimpse into just how massive the molecular world really is, all thanks to his work with diffusion.
It's amazing to think about, we started with those ancient Greek philosophers debating the very nature of matter, and now here we are diving into the world of molecules, these tiny things we can't even see, but they make up everything around us.
It really puts things in perspective, doesn't it?
It does, and it makes you realize how far we've come in our understanding.
Speaking of incredible discoveries, those articles you sent about this lake molecule,
Oh, yeah.
really fascinating stuff.
It is. It is. It's amazing how this whole deep dive has connected these seemingly totally different things. Like, we've got these fundamental concepts of molecules from, like, way back when.
Right.
And now this cutting edge research into something like lake. It's incredible. So how does this new molecule actually work?
Well, at its heart, lake still relies on those same basic building blocks that Clerk Maxwell was describing. Oh, yeah. Just shows how much there still is to learn about how those blocks can be arranged and how they interact,
So even though lake is this synthetic molecule, it's still playing by the rules of chemistry that have always been there.
Exactly. It's a testament to the power of understanding those fundamental principles. And the really ingenious thing about lake is that it mimics the effects of exercise and fasting.
Oh, interesting. Like, it tricks your body into thinking you've been hitting the gym.
Basically. You see, exercise and fasting, they naturally increase the levels of certain substances in our blood.
Okay, what kind of substances?
The key players here are lactate and ketones.
Okay.
lactate,
Right.
that's produced by your muscles when you exercise. It's what causes that burning sensation when you're really pushing it.
Right, right.
And ketones, those are produced by the liver when we fast or really cut back on carbs.
Okay.
They basically act as an alternative fuel source for our cells.
Interesting. So Lake is like, hey, cells, look, exercise and fasting benefits, no work required.
That's the idea. And those studies you sent, that one from the University of Chicago, is really eye-opening.
Yeah, they were talking about some pretty incredible potential benefits, reduced risk of heart disease, stroke, type 2 diabetes, even helping with brain trauma.
It's all very promising. We got to remember, these studies were done on rats.
Right, of course.
Human trials are happening, but it's still early stages.
Still, it's pretty amazing to think that by understanding those fundamentals that Clerk Maxwell was wrestling with, over 100 years ago,
Yeah.
we're opening the door to these kinds of breakthroughs.
It really highlights the power of scientific curiosity, doesn't it?
It does. Who knows what we'll uncover next? That's the beauty of it all, isn't it?
Absolutely. Always more to learn, more to explore.
And who knows what amazing discoveries await us in the future?
I can't wait to find out.
Me neither. Thanks for joining us on this deep dive into the incredible world of molecules. It's been a wild ride. Until next time.